and welcome to Lecture 10 on Computer-Aided Engineering Design. This lecture is on transformations of solids. We will start from where we left off last time. We were discussing two-dimensional rigid body transformations. We had this matrix A, if you remember, which had 9 elements: A, B, C, D, E, F, G, H, and I. This was a 3 by 3 matrix that represented a generic two-dimensional transformation. We applied this transformation on, say, a solid of which, let's say, we have these two edges represented by vectors v1 and v2. Recall that when performing rigid body transformation, the lengths of these vectors do not change, and also the angle between these two vectors remains constant. We had incorporated both these conditions in terms of the dot and cross product between the two vectors. We said that before and after rigid body transformation, the dot products did not change, and also the cross products remained the same. When we applied these constraints on the dot and cross products, we came up with the following conditions on the elements of this transformation matrix. The first one was that a squared plus d squared equals 1. The second was that b squared plus e squared equals 1. The third was a times d plus b times e equals 0. And the fourth was a times e minus b times d equals 1. We had additional conditions. G, this element here, equals 0, and h equals 0. We did not say anything about the element I. If you look at these 4 conditions, they involve this submatrix of A. In a sense, the 4 terms A, B, D, and E. If I write this submatrix of A as A1, then last time we found that A1 is orthogonal. In other words, the inverse of this 2 by 2 matrix A1 was the same as the transpose of the matrix, or A1 times A1 transpose was the same as A1 transpose times A1, and this was equal to a 2 by 2 identity matrix. If we look at rotation and reflection matrices, the cases that we had discussed in lecture 9, we find that rotation and reflection matrices are orthogonal. However, translation is not an orthogonal operation. In that case, the vectors do not change. Let's go back to these conditions. Once again, these four conditions relate these four elements of a generic transformation matrix A in 2 dimensions, and we have information about these two elements as well, G equals 0 and H equals 0. We do not have any information on I, and also we do not have any information on C and F. But that's not true if we look at translation matrices. C would be an element that would represent translation along the x coordinate, and F would be an element that would represent translation along the y coordinate in the xy plane. Now let's discuss deformation transformations. These are the transformations if applied to solids will deform solids. Going back, the vectors will no longer have the same magnitude, and also the internal angles between the vectors would change if we apply deformation transformations. The first of these is a scaling transformation. Let's say we have a position vector P with coordinates x, y, and 1, and of course these are the homogeneous coordinates. We can scale the x component individually and the y component separately. Mu x and mu sub y will be the two scaling factors. So this 3 by 3 matrix represents the scaling operation. In short, that is represented by S. It is not very difficult to note that if we pre-multiply this column vector by the scaling matrix, we will get x star as mu sub x times x and y star as mu sub y times y. X star and y star will represent the scaled position vector P star. We can go for either uniform scaling or non-uniform scaling, and here is an example. If we set mu x equals mu y, we will then have a case of uniform scaling. Scaling will be the same in both orthogonal directions x and y. If, however, we set mu x and mu y to be of different values, then we'll have a case of non-uniform scaling. The second of the deformation transformations is shear. Let's say that we want to shear an object along the x direction. An object will have vertices, each of which will be represented by this column vector. In short, by P, and this 3 by 3 matrix over here would represent a shear transformation. Once again, shearing is happening along the x direction. This 3 by 3 matrix will have components 1 sh sub x 0 0 1 0 0 0 1. If we pre-multiply this column vector with this shear matrix, we have x star as x plus sh sub x times y, and y star as y, the original coordinate of point P. And of course, x star and y star are the new coordinates P star. Realize what has happened to the new x coordinate. It has, of course, altered to a new value x plus sh sub x times y. The y coordinate, however, remained the same. Once again, this is a case of shear along the x direction. If we want to shear a two-dimensional object along the y direction, we need to make minor modifications in the shear transformation matrix. Here, we would be introducing a shearing factor sh sub y in the first column and the second row. So, for shear along the y direction, the transformation matrix is 1 0 0 sh sub y 1 0 0 0 1. Let us see what happens when we pre-multiply the column vector x y 1 with this transformation matrix. Multiplication is trivial. So, x star would be x. The x coordinate of the transformed point does not change. Y star will be sh sub y times x plus y. It is the y coordinate that would change. In short, this transformation matrix that shears a point along the y direction is represented by sh sub y. And of course, these transformations, they act on points P. A few examples of shear: on a rectangle with coordinates 3 1 3 4 8 4 and 8 1, if we apply shear along the y direction with the shear factor sh sub y as 1.5, we will get the new coordinates P1 star, P2 star, P3 star and P4 star as the common shear matrix. Note that this is the shearing factor that appears over here, and this common shearing matrix will be pre-multiplying the original coordinates. The results are 3 5.5, 3 8.5, 8 and 16, 8 and 13. The new coordinates after shear transformation along the y direction is performed. Notice how this original two-dimensional object is changing both in shape as well as size. If you notice carefully, there is also a component of rigid body transformation. Now let's try to generalize two-dimensional transformations, and let me also use this opportunity to generalize transformations in 3 dimensions as well. In general, two-dimensional transformation matrices are of size 3 by 3, and those in 3 dimensions, they are of size 4 by 4. It is possible for us to subdivide both these transformation matrices into 4 different sub-matrices. The top left submatrix is of size 2 by 2 in case of two-dimensional transformations, and for 3 dimensions, this top left submatrix is of size 3 by 3. These submatrices contain entries pertaining to rotation, reflection, scaling, or shear transformations. We had noted in lecture 9 that this 2 by 2 submatrix is orthogonal in nature. That is, this matrix times its transpose is equal to an identity matrix of size 2 by 2. Similarly, in case of 3 dimensions, this 3 by 3 matrix is also orthogonal. Well, when I say that they are orthogonal, I am referring to rotation and reflection cases. In case of scaling or shear, these matrices will of course not be orthogonal. The top right sub-matrix in case of two-dimensional transformations is of size 2 by 1. In case of 3 dimensions, this top right submatrix is of size 3 by 1. We have seen before in case of 2 dimensions that these 2 elements represent translation along the x coordinate and along the y coordinate respectively. In case of 3 dimensions, these 3 elements would represent translation along the x, y, and z coordinates. In summary, the top right matrices will contain entries that pertain only to translation. The bottom left submatrix, which is of size 1 by 2, so we have 2 elements here, A31 and A32, and correspondingly in 3 dimensions, the bottom left matrix that has 3 elements. These submatrices represent perspective transformation. We will investigate perspective transformations in detail in the following lecture. In general, if we are not referring to perspective transformations, these entries will be 0. But otherwise, if we are viewing the perspective image of an object, these entries will be non-zero. The bottom right submatrix in both cases, in case of 2-dimensional and 3-dimensional transformations, is of size 1 by 1. In fact, these matrices are simple scalars. And in fact, these elements represent global scaling. They are also called homogeneous coordinate scalar. In summary, any 2-dimensional transformation will have the size 3 by 3. This matrix can be subdivided into 4 parts. The top left will represent rotation, reflection, scaling and shear. The top right will represent translation. The bottom left will be invoked in case we need to view an object in its perspective transformation, and the bottom right number is used essentially when we are performing global scaling. In case of 3 dimensions, the 4 submatrices have identical meanings, just that their sizes are different. Let's study transformations formally in 3 dimensions. We first study translation. A translation matrix in 3 dimensions is represented by a 4 by 4 matrix with this submatrix as the identity matrix. We have the top right submatrix or the column vector with non-zero entries. These entries are 0 and this 4th by 4th entry is 1. P represents translation along the x direction, Q the translation along the y direction, and R translation along the z direction. This is an example of this toroid being translated from this position to this position along this vector. Rotation in 3 dimensions. Let's first try to figure the rotation matrix if we are trying to rotate an object about the z axis. This is a 4 by 4 matrix with entries cosine of theta minus sine of theta 0 0, sine of theta cosine of theta 0 0, 0 0 1 0 and 0 0 0 1. No translation and no perspective, and the global scaling factor is 1. You can verify that the top left part of this matrix is orthogonal. This is the way I remember when I jot down rotation matrices about different axes. For example, if I am to rotate an object about the z-axis, I will have the entry 1 in the 3rd row and the 3rd column, and then I will start putting in cosine of theta minus sine of theta, and cosine of theta in the corresponding x and y entries, which are of course the first and second rows and the first and second columns. When I do that, I do not forget the cyclic order: x, y, z, y, z, x, and z, x, y. If I maintain this cyclic order of coordinates, I will hopefully not make a mistake in writing the cosine and sine terms. Let's try this for a case where I'm trying to rotate an object about the x-axis. As we did here, we will have an entry 1 corresponding to the x row, that is the first row, and the x column, that is the first column. And then I'll start writing the cosine terms and sine terms, maintaining the cyclic order of the x, y, and z coordinates. So my cosine term will be in the second row and second column, and minus sine psi, this term will be in the second row and third column. And then for the rest, I'll have sine psi and cosine psi. All the other entries will be 0 except for this 4th by 4th entry, which is 1. Let's try the same for a case when I'm trying to rotate an object about the y-axis. You already have the result in front of you. The entry corresponding to the second row and second column will be 1, and then I have to maintain the cyclic order. So after y comes z, so I'll have cosine of phi here, and in the same row I'll have minus of sine phi in the first column, and then I'll have sine phi term here, and the same row, first column, I'll have cosine phi. All the other entries will be 0 except for this entry. If you practice a little bit and if you understand the concept, writing rotation matrices in 3 dimensions is not difficult. This is an example of an object being rotated about an arbitrary line L that passes through the origin. We'll study rotations about an arbitrary line formally in the following slides. So this is the problem statement. Given direction cosines n, which has components nx, ny, and nz of a line that passes through a point P, Q, and R. Now this point here is expressed in terms of homogeneous coordinates. If we are to rotate an object about this line, we'll have to follow some steps. The first of them is to translate the line such that it passes through the origin. And to do that, we have to apply this transformation. Notice the negative signs here. So that brings us to the case where we have translated this line that is represented by OU, so that one end of this line is sitting on the origin of a three-dimensional coordinate system. Let's draw a block around this line. So nx is this magnitude here, ny is this length here, and nz is this length. OU is one of the diagonals of this block. Let's project u to a point u, y, z on the y, z plane. Let the distance between O and the point u, y, z be d. In terms of the direction cosines nx, ny, and nz, it is not very difficult to find what d is. D is ny squared plus n sub z squared raised to half. And since the direction cosines are such that nx squared plus ny squared plus nz squared equals 1, d is 1 minus nx squared raised to half. Let's mark this angle and name it as psi. Then cosine of psi is n sub z over d, n sub z over d, and sine of psi is ny over d, ny over d. Just in case if I am boring you, you can always pause me and go for a tea break or a coffee break and resume the lecture after 5 or 10 minutes. What I am going to be saying would be important. If I rotate line O, u, y, z about the x-axis, what will happen? Well, you guessed it right. O, u, y, z will coincide. That is not the same as the original line OU coinciding with any of the principal axes. We'll come to that later. But if we perform this rotation, that is, rotate OUYZ about the x-axis such that OU lies on the xz plane. I already said it. Once I rotate this line, OU will lie on the xz plane, and OU YZ will coincide with the z-axis. U prime is the new position of U, and U YZ prime is the new position of U YZ. The corresponding rotation matrix will be Rx equals 1, 0, 0, 0, 0, NZ over D minus NY over D, 0. Note that these two terms are the cosine psi and sine psi terms each, respectively. The third row will be 0, and y over d, and z over d, 0. And of course, the final row will be all 0 except for the 4th by 4th entry, which is 1. Now, to make the line OU prime coincident with, let's say, the z-axis, it becomes a little easier for us. O u prime yz is coinciding with the z-axis. Remember, we have performed rotation previously, so this length will remain d. The direction cosine nx will not change because the previous step was rotation about the x-axis. All we need now is to rotate O u prime by an angle phi about the y-axis so that the line coincides with the z-axis. What is phi? From trigonometry, this angle is 90 minus phi, and so the cosine of this angle is nx over OU prime, the length of which is 1. In other words, cosine of 90 minus phi equals sine of phi, which is nx, and cosine of phi will be 1 minus nx squared, the entire thing under rooted, which is d. Well, once we have the cosine phi and the sine phi terms, all we need to do is to construct a rotation matrix about the y-axis. I would want you to stand on this arrowhead and figure out how, whether clockwise or anti-clockwise, would OU prime be rotated about the y-axis. You guess it right. It will be clockwise. I've already said this. Rotate OU clockwise about the y-axis such that OU prime coincides with the z-axis. So if we consider the rotation matrix Ry, we'll have 1 in the second row and the second column, and then we'll have cosine, minus sine, sine and cosine terms. And remember, this is minus phi here. Why? Because we are rotating this line clockwise about the y-axis. Once we have the line coinciding with the z-axis, all we need to do is perform the requisite rotation about the z-axis by, let's say, a desired angle alpha. We know the rotation matrix for that. Rz is cosine of alpha minus sine of alpha 0, 0, sine of alpha, cosine of alpha 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Now, we place this line back to its original position. How do we do that? We perform back transformations similar to the example we saw in a two-dimensional case. If I consider the overall transformation process, this is how it will look like. Once again, recall that I have to go from right to left. First, we perform translation to make a point on the line coincide with the origin. Then we perform rotation about the x-axis by an angle psi, and then we perform rotation about the y-axis by an angle minus phi, which is clockwise. By this time, the line is coincident with the z-axis. We perform the rotation about the z-axis, which is equivalent to performing rotation about the desired line, and then inverse transformation or inverse rotation about the y-axis by minus phi. That will bring the line from the z-axis back to OU prime, and then inverse transformation or rotation about the x-axis that would orient the line in its previous orientation, and then translating one of the points on the line back to its original position. Right? to left. A little bit of practice and this will be clear to you. Let's quickly construct a few more transformations in 3 dimensions. Reflection. If we consider reflection about the xy plane, only the z coordinate changes sign. The x and y coordinates remain the same. Accordingly, our f sub xy, reflection about the xy plane, will be a 4 by 4 transformation matrix, which will look like this. Entries 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1. Note the sign change in the z coordinate, and 0, 0, 0, 0, 1. Likewise, reflection about the yz plane will make the x coordinate change in sign. Reflection about the yz plane will be a 4 by 4 matrix. Well, you can consider it to be an identity matrix with the difference that the first term here will be -1. Finally, reflection about the zx plane, for which the y coordinate will change sign. Our f zx, reflection about the zx plane, will be a 4 by 4 dimensional matrix. Again, very similar to an identity matrix, but with the second by second term here as -1. Deformation in 3 dimensions. First, scaling. The scaling matrix S looks like this. The scale factors mu x, mu y, and mu z are in the positions 1, 1, 2, 2, and 3, 3 on the principal diagram. These are non-zero values, and this scaling matrix is equivalent to this one, with elements in the first row as 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, s. This equivalence happens under special circumstances. When the scale factors mu x, mu y, and mu z, they are all equal, say, to mu, and mu equals 1 over s. Let me explain the equivalence on board. Let's say the homogeneous coordinates of point P are x, y, z, and 1. If I multiply this column vector by s, this would give me Sx, Sy, Sz, and S. In homogeneous coordinates, the column vector Sx, Sy, Sz, and S would represent the same point as x, y, z, and 1. We say that these two column vectors are equivalent because these represent the same point in the Cartesian or in the 3-dimensional space. Noting the equivalence in homogeneous coordinates, we see the following. The leftmost column indicates the new position P star. This matrix is obtained by making all the scale factors equal to 1 over s. if I pre-multiply the old position of the point by this scaling matrix or uniform scaling matrix, I get x, y, z, and s. And we have seen before that this column vector is equivalent to this one. If I divide the entries in this column vector by s, I'll get x over s, y over s, z over s, and 1. And this will be similar to multiplying the original position of the point by this 4 by 4 matrix with entries 1 over s at the 3 positions of the principal diagonal. The next is shear transformations in 3 dimensions. The generic transformation matrix for shear is given by this 4 by 4 matrix with entries 1, sh sub 1 2, sh sub 1 3, 0, sh sub 2 1, 1, sh sub 2 3, 0, sh sub 3 1, sh sub 3 2, 1, 0, and the fourth row we have all these entries as 0, and the last entry is 1. These entries are non-zero, and they result in shears along various directions. These 2 entries will result in the shear along the x direction, these 2 along the y direction, and these 3 along the z direction. We can check this out by multiplying the column vector of the original point x, y, z, 1 by this 4 by 4 matrix to get the new position. This multiplication is quite straightforward, and once you multiply, you would see that the first entry x star corresponds to x plus sh sub 1 2 times y plus sh sub 1 3 times z, making these 2 non-zero entries affecting the shear along the x direction. The second entry y star is sh 2 1 times x plus y plus sh 2 3 times z. These 2 entries resulting in shear along the y direction. The third entry z star is sh 3 1 times x plus sh 3 2 times y plus z. These 2 entries here resulting in shear along the z direction. And the fourth entry, of course, is 1.